Okay, so let's finish up that lab from on the limb. And so if you look at, the technology that they had to develop and the engineering struggles that they had to go through to get us to the moon, it was daunting. And even like the navigation part to the moon, it's like, okay, so short version is, this is the very, very short version, is that they orbited the Earth a couple times to make sure everything was cool. Then they fired the rocket engines to get them on a trajectory towards the moon. Now, and the moon wasn't stationary, okay? The moon's moving because it's in orbit around us. So it isn't like you can, aim for the moon and there it is. It's just like if you're throwing a pass. You don't throw where the receiver is, you have to figure out where the receiver is going to be when you throw that pass. And the same thing we had to do with the moon. So, kind of to give you some scale, imagine that you're standing on one end of a football field and you have to shoot an orange that's at the other end of the football field, but the orange is moving and you don't want to hit the orange, you just want to nick the skin on the side of the orange from 100 yards away on an orange that's moving. That gives you some scale of what you had to have. So, and the computers weren't all that good at the time. They were just kind of developing, like the kind of first generation of computers. And they got towards the moon. They had to slow down, get caught in the orbit. Then they had to undock the Lunar Command Module, which is what you guys did. Would go down to the moon, land. Then you had the service module, which would continue to orbit. Then they had to leave the surface of the moon, redock with the service module, fire the engines, come back to Earth, boom, and then when you went into the re-entry of the Earth, if like the Earth is the size of a basketball, they had to hit a corridor about the size and the thickness of the edge of a piece of paper. Because if they don't hit that just right, they come in too steep and they burn up because they're slowing down too quickly. If they're too shallow, they hit the atmosphere of the Earth,
bounce off,
and they'll just skip off like a stone. And so they had an extremely small, so nothing about this was easy. And they all had, basically all this stuff had to be invented right from the get-go. So, make sure on that, on questions 5 and 6, here's how you can check that your answer is right. On that last page. Take what you think the applied force is, whatever that number is. So let's say you think the answer to number 5 is around 3,000. Okay? So keep this in mind. You're trying to find the applied force. And remember this for the lab today and going forward. By the way, y'all are having a quiz tomorrow. Not a test, a quiz. Okay?
panic.
Just saying. Like over kind of Newton's laws, net force, calculations, that type of thing, friction, accelerated motion versus constant velocity.
Can we go in the test category or the assignment category?
It's going in the test category, but it's just going to be a small, won't be worth a lot of points. Yeah, that doesn't say, oh, I don't need to study. So I'm just saying. So remember this, that net force equals force applied plus force opposing. Which of those three is the only one that equals mass times acceleration?
Force net.
Net force. Okay, you remember that for the lab today. So if you look on number 5, you want to know how much force must the engines produce. So when you see how much force must the engines produce, am I asking you to find the net force, the applied force, or the opposing force?
Applied.
Yeah, this is what you don't know. You're searching for the applied force. Okay? Now, think about this. You want an acceleration of negative 1.1 meters per second squared. So right away, you know your applied force has to be less than your opposing force because you know you want a negative net force. So you know that applied force has to be less than 8350. Okay? Because if it was greater than 8350, you'd have a positive net force, you'd have a positive acceleration. So before you do any calculations at all, you can look at that and go, okay, well, my applied force, it still has to be a positive value, but it has to be less than the 8350. You still have that same mass, so you can take, oh, here's my mass times my acceleration, ma, boom, there you go. Okay, you have the mass, still 5,000 kilograms, you have that acceleration of negative 1.1, that's gonna get you your net force. Your opposing force is gonna be that same mass times negative 1.67 meters per second squared, because we're landing it on the moon, okay? And your applied force is what you don't know. So basically, subtract that over. Pay attention to the negative signs, okay? Pay attention because you're subtracting in effect a negative value. So let's say, again, you think the answer to number 5 is 3,000. Take that 3,000 as your applied force, add a negative 8350 to it, find your net force, divide that by 5,000 kilograms and see if you get an acceleration of negative 1.1 meters per second squared. If you did, at least you have a fighting chance if you did it right. If you don't, I promise you it's wrong, okay? So that's how you can check that your answers to 5 and 6 are right. Okay, on that velocity time graph, make sure I, not you, make sure I can clearly see when it's speeding up, when it's slowing down, when there's a positive net force acting on the system, and when there's a negative net force acting on the system. Okay? Go to sneeze or a cough.
That was 2 coughs.
Oh,
You can tell my coughs versus my sneezes because I don't breathe in a lot before I cough, but I do before. If I feel a sneeze coming on, it'll be much louder, I promise.
okay. Duly noted. Anyway, anything else on that lab? Going once, going twice. So get that hand in. Someone stop that camera for a second.